Yeah. Okay, so thank you everybody for coming for today's One World Fractals meeting. Our first speaker is Katrin Gelfert from Rio, and she'll talk about the amount of non-hyperbolicity in partially hyperbolic diffeomorphisms.
Okay. Well, thanks for inviting me to speak. I'm really apologize that I wanted to use a tablet, but it doesn't work. So I'm talking about some piece of recent research with Lorenzo Diaz and Xinhua Shang, and also with Mira Rams. But the thing I'm talking about is the precursors were with Mira, but work is only with these two. It's about partially hyperbolic diffeomorphisms. So some parts of the things are not so much fractals, but I hope that you get some interesting ideas from this field of math. So I start with a few general questions. So we wanted to understand systems which are not uniformly hyperbolic, a general diffeomorphism maybe in the future, who knows? And the first question arises, what is non-hyperbolic behavior? So what is going beyond the uniformly hyperbolic? And our focus is on measures, or well, naturally the Lyapunov exponents come into play. So you could ask, we could characterize this in three ways. For example, the existence of an ergodic measure with zero exponent, with one of the Lyapunov exponents being equal to zero, or the existence of points with one zero Lyapunov exponent, which is not necessarily equivalent to the first, or the existence of ergodic measures with non-zero Lyapunov exponents, but whose exponents converge to zero. The existence of a sequence of ergodic measures whose exponent converges to zero. And in some context, well, these three types of definition of non-hyperbolic behavior are a priori distinct. They will be satisfied, all the three of them in our context. And we're trying to quantify non-hyperbolicity. And then, well, one way is, of course, looking at measures, non-hyperbolic measures and their entropies, and another one is looking at points with zero Lyapunov exponent, the set of points and their size. And here I will be talking about the entropy of the set of points with this type of behavior. You could also look at Hausdorff dimension, but for the time being, it is the topological entropy of these vector sets. So I will be talking about, this is my setting. I will look at partially hyperbolic diffeomorphisms on a manifold dimension at least 3. So partially hyperbolic means that the tangent space splits into 3 bundles. One is uniformly contracting, one is uniformly expanding, and then there's a third bundle in the middle, dominated from the others. And here I assume that it's one-dimensional. Hence, if you restrict to this one-dimensional bundle and look at the infinitesimal growth, this defines a continuous function. And when you integrate this against an ergodic measure, we call this a center Lyapunov exponent. So this is, in this case, it's one of the Lyapunov exponents from the oscillated splitting. And so the other two bundles have negative and positive Lyapunov exponents. I will disregard them. Maybe you could do a joint multifactor analysis looking at all of them at the same time, but not here, not now. And I will only look at the behavior in the central direction. So that could be negative central Lyapunov exponents, zero Lyapunov exponents, or positive ones. And all these cases will appear in the setting I'm looking at. Okay, let me start with some precursor, an easier model. And indeed, we studied first these type of systems to develop some tools. Then eventually we went to understand diffeomorphisms. But indeed, the system I will describe now has very much to do with some features are very much the same as in the general case I will be presenting. So look at the following case. Take two circle diffeomorphisms, F0, F1, okay? And then, so your one is, for example, a North Pole-South Pole map. So it's a map on a circle with one repelling fixed point, let's say the South Pole, one rectangling fixed point, the North Pole. And F1 is an irrational rotation. Okay, then you look at this Q product that you take your favorite coin with two symbols and apply in the first coordinate the shift, and the second coordinate one or the other of the circle maps, depending on the symbol on your shift. Okay, so for example, and here you have a mixture of behavior. For us, the relevant behavior is in the circle, which is the fiber, which would correspond to the behavior defining the center Lyapunov exponent or the Lyapunov exponent in the fiber. So for example, you have for this point an attractor. You have in the fiber contraction. This point is contracting. And the Dirac mass there would correspond to a measure with negative exponent. Then you have a repeller. The South Pole defines a point and a Dirac mass with positive Lyapunov exponent. Or if you just look at points and apply the symbol 1 in the base, then you have neutral behavior, and every point defines, if you take some limit measure defining an ergodic measure, that you have 0 Lyapunov exponents. So you have all three types of Lyapunov exponents in this case. And the corresponding fiber Lyapunov exponent would be defined this way. It's expansional growth of the derivative of these concatenated maps. Okay, so you have the range of exponents, some negative, some positive value, and 0 in the middle. And indeed, for this example, it would be a closed interval. Okay, so there is one important ingredient which I will put as a hypothesis later on, which is the following. So suppose that you have three maps, one North Pole, South Pole with South Pole, one North Pole, South Pole map with the South Pole here, and another one with the South Pole is slightly dislocated. You could get this, for example, from the first map and applying one of the rotations a few times. Okay. Then if you look at these two repelling fixed points, there's an overlap of these branches. And if S prime is very close to the other one, this overlap will happen really like it is in the picture. This is an example, a very simplified example of a blender, what we call a blender horseshoe. In this case, it's center unstable because they're repelling. So it's a center unstable blender horseshoe. And if you would look at the inverse maps, this would correspond to a center stable blender horseshoe. Okay. This is a very useful machine. Indeed, this was developed since long time ago principally by Christian Bonetti and Lorenzo Diaz to study robust behavior for diffeomorphisms. And very roughly speaking, it's a machine that enables you to stay close to a repeller. So a repeller usually repels you, but because you have these two repellers, you can apply one or the other map and stay within this region where you have expansion in a controlled way. Okay, so this is one ingredient which will enter as a hypothesis in my result, and it is satisfied for example in this precursor, in this skew product case. Okay, so let me state the hypothesis I will assume. So I look at C1 diffeomorphisms. It should be transitive. As before, I said already that I assume that there is a partially hyperbolic splitting, stable, unstable bundle. I focus on the one-dimensional center bundle, trying to do a multifractal analysis of this corresponding potential function. The stable and the unstable bundle, because of uniform hyperbolicity, they define minimal foliations. They are the strong stable and the strong unstable minimal foliation. A minimal here means that each leaf is dense in the entire manifold. And then I assume that there exist these blender horseshoes of each type. And if you, they're very roughly the same thing as this. It's a special type of horseshoe which has this overlapping property. And I would like to have two of them, one of one type and one of the other type, where the type corresponds to the expansion in the central direction. We call these classes blender minimal of C1 diffeomorphisms. And there's indeed a big class of examples. For example, the circle fibered, let me see if this works. So the circle fibered would be perturbations of Anosov times the identity, and you could think that this is very similar to this abstract precursor. So you have your Anosov in the base and the fiber maps, which are the circle fibers. Okay. Then there are of flow type, so roughly speaking, perturbations of an anosov flow. The time one map of an anosov flow is a partially hyperbolic, so take perturbations, you keep the partial hyperbolic structure, and you get into a class of examples. Then there are some DA diffeomorphisms, and then there are also some non-coherent examples. So if you want to have references in the preprint, we dedicate an entire section to discussing examples. And there are really plenty. There are open and robust classes of examples where these hypotheses are satisfied. Okay, so multifractal analysis, the amount of non-hyperbolicity. Yeah, I'm sorry, I wanted to use the pen on the tablet now, so this doesn't work. So I fix a value of central Lyapunov exponent. For example, here this is I fix a value 0, but instead of 0, you could write here any alpha within the range of possible exponents, and it's just a set of points where this growth rate is equal to alpha. So in this formula, it's equal to alpha equal 0. Okay. And then I would like to see how big this set is, how many points there are with this behavior, and my quantifier in this talk is entropy. So I look at the topological entropy on this set, following Bowen's definition. Okay. And as you're very the parameter alpha, you could look at this function h of alpha, which is the entropy on this each level set. Okay. So there are precursors with previous results that understand this function. And this figure is for the special example of this Q product or the corresponding figure in the diffeomorphism case. So in this case, there are two measures of maximal entropy of different type of hyperbolicity. And what is important in this figure is there are two concave parts. There are two continuous functions, and these two functions meet in the middle. So these are universal properties for all functions in this case. H0, the point where they meet, is positive. Okay. But if it's less than the maximal value, this depends on the classes. The type of measure of maximal entropy could depend on the classes. For example, in a DA, there's only one, which is of one type, depending on the DA derived from anosov diffeomorphism. And there are further questions to be answered. Okay, I would like to focus on this H0. So H0 is the topological entropy on the level set with 0 Lyapunov exponents. Okay, and this is my theorem. So assume the hypotheses, these Blender minimal C1 diffeomorphisms. Then this value H0 is positive, equal to the entropy of the Lyapunov exponents, the set of points with 0 Lyapunov exponent. Okay, and moreover, there is a subset L of 0, and I would like to give some ideas on how to construct this, satisfying the following properties. It is foliated by curves tangent to the central direction, so there are some pieces of curves. But in the transversally, it's a kind of Cantor set. It has maximal possible value of topological entropy, and the convergence to the 0 Lyapunov exponent is uniformly on this set. Well, as the talk, I'm not giving too many references. There's, of course, previous results by Diaz-Gorodetsky, for example, proving that this value H0 is positive. By Diaz-Gelfert and Santiago to prove certain approximation results of non-hyperbolic measures by horseshoes, and also Jiagang Jiang and Xiang, they have work on this. And to understand this figure, to prove that these two curves meet in the common point, you need to prove, and this was done in previous work. Okay, so in this talk, I would like to give some ideas how to construct lambda 0. Okay, there are two ingredients. Concatenation of center curves, and I hope that this is of some interest to this audience. And then there's a bridging measure tool to estimate entropy. Okay, so let me just start with the concatenation of center curves. This is a slightly technical ingredient from smooth dynamics. So the central direction is one-dimensional. It's a continuous line field. So they exist by Peano's theorem. There exist curves, say gamma, which are tangent to this line field, not necessarily uniquely defined, but such curves exist. And then you foliate them. In each point, you attach one piece of unstable manifold from this foliation, and you fill up this curve. So this gives a piece of manifold which is tangent to these two subbundles. This is not automatic. That's a result by Brin, Boragov, and Ivanov. So they define weak foliations. And then you can do the same thing for the stable foliation. You foliate by stable pieces. Okay, so you take one of these pieces of weak foliation. Let's assume that X is a point in gamma where you have 0 Lyapunov exponent. Such points exist because you have plenty of measures with positive and negative Lyapunov exponent. And you look at iteration of this piece of manifold. So it will stretch in the unstable direction. And because the foliation is minimal, these images of these leaves eventually intersect any open neighborhood. Let's say given another piece of this weak foliation by using minimality. And indeed, this number of iterations you would need depends on the size of these pieces, but they can be chosen uniformly over the entire space. Okay. And then you concatenate. So you take one piece, one curve, gamma 1, where it has a point, say, of exponent alpha, negative. And I would like to construct a counter set of points with 0 exponent. So I take a sequence of curves with exponents, say, alpha over 2, alpha over 4, etc., etc. Such points exist because of the existence of plenty of measures with Lyapunov exponent converging to 0. So I take one curve gamma 1 and one curve of gamma 2. Okay. And then I concatenate. So the iterate of this leaf will be stretching, will be wiggling around your space. And I can do the same thing with this weak stable foliation, iterating backward. It will also stretch and will wiggle through the space. And then now comes in our technical ingredient, the Blendor horseshoe. Indeed, this is a center stable Blendor horseshoe, so it would be an unstable Blendor horseshoe for the inverse. And it says a certain finite size, so these leaves eventually intersect. And I can stay in this Blendor horseshoe and expand under the inverse maps to increase the size of these manifolds in the central direction such that they, in finite time, can intersect. So here, this red thing will eventually intersect an iteration of the blue piece of leaves in some curve, which is a center curve. So here I will get in this intersection a blue curve, which I now can pull back into a curve here in the original piece of leaves. So what this blue curve does what? It follows very closely this first exponent alpha, but eventually it would move close to the point to points on the curve where the exponent is alpha over 2. So I constructed orbits which have exponent first alpha, eventually alpha over 2, and so on and so forth. Okay, and this is the principal idea. Now I start by choosing a cascade of curves, say just one with exponent alpha negative, and then a set of curves, a collection of curves with exponent, say, alpha over 2, a set of curves with exponent alpha over 4, and so on and so forth, such that their Lyapunov exponent converges to 0. And I choose such that each collection has a cardinality according to some ergodic measure whose exponent converges to 0, such that their cardinalities approach this number h0. And let me just go back for one moment to argue why such measures and such points exist because of this figure. So if I have this value, we prove that any of these values can be indeed approximated by the exponent of ergodic measures whose entropy is very close to this number. So I find a sequence of ergodic measures with negative central Lyapunov exponent whose exponent is converging to 0. And once I have an ergodic measure, I know that generic points with certain behavior grow exponentially. So I can find plenty of points whose exponent is negative and converging to 0. So these cascade of curves exist. So let me just take gamma 1 and say one of these curves, gamma from this second collection. And I do this concatenation procedure. I get a blue curve here, and I pull this blue curve back together with some neighborhood. Okay, and then I forget about this construction. I focus on this second curve and take a curve gamma from the third collection. I get an intersection curve. I pull this back. I pull this back. And now I do this for any of these curves in this collection 2 and this collection 3 and so on and so forth. So I construct here in this first beginning leaf, initial leaf, a counter set of curves, and points in these curves have the property that their orbits first follow the first exponent, then follow the second exponent, then follow the third exponent, and so on and so forth. So we here in this leaf construct a limb subset of points whose Lyapunov exponent in the limit is equal to 0. So this is the construction of the set lambda 0, which was in the statement. So, and the final step is to estimate their entropy. We use an entropy distribution principle, which is analogous to the mass distribution principle. Indeed, here there's a version in the paper Takens-Verbitsky from 2003. So, and we do this by constructing what we call the bridging measure. So it's in this case, it's a limit of equidistributions on these curves which were pulled back here. And you use the entropy distribution principle on this measure to prove that the entropy of this set of points where the measure is supported is equal in the limit to this value h0. And this is the rough sketch of the proof. I hope that I could explain some ideas. Okay, thank you.